The title of this work is Resource Performance Trade-off Analysis for Mobile Robots, and the focus is to aid designers in choosing robot components according to the required performance of the robot. Mobile robotics is a fast-growing field, and the main feature that makes these robots attractive is their ability to operate remotely with some level of autonomy. But from the design point of view, the very same feature introduces a major challenge because only a limited amount of resources is available on board. Autonomy is enabled by several modules such as localization, perception, and planning. To achieve the best performance, today's robots run all these modules simultaneously and continuously, which is very expensive on the resources. Our key idea is to intelligently schedule these modules, which of course results in a trade-off between resource usage and the performance of the robot. Our goal is to compute the set of all optimal resource performance trade-offs, also known as the Pareto curve, to aid the designer. To this end, we formulate a problem where a robot moves in an environment by following a reference trajectory in the form of a series of waypoints. The resource usage of the robot is given as a cost function, and we want to schedule the use of the localization module according to the resource performance objectives. Note that when the localization module is not used, the robot only knows a rough estimate of its location, which can cause a deviation from the reference trajectory. And if the robot continues without localizing, it could possibly collide with an obstacle or miss the target. But when the localization module is used, the robot gets an accurate estimate of its location and can try to get back to the trajectory. Therefore, the problem becomes multi-objective optimization, where we want to maximize the probability of reaching target, minimize the probability of colliding with an obstacle, and minimize the expected total resource cost. Note that this is a very challenging problem because by nature it requires reasoning in the belief space, which is known to be a computationally infeasible domain. To approach this problem, we first design appropriate control laws to enable the robot to follow the trajectory with some guarantees in the belief space. Then we construct the corresponding belief graph, which is very large in size. It is in fact exponential in the number of waypoints. Through a novel technique, we turn this graph into a Markov decision process, which is only quadratic in the number of waypoints. Then we can pass this model to our multi-objective verification tool and obtain the Pareto curve. Then, given the designer's choice of a Pareto point, our tool is able to compute the corresponding optimal scheduler. We evaluated this framework on a planetary rover in both simulation and experiment and got very powerful results, including some surprises. Come to our poster to talk about the details of the method and see the results.